Hello, this is Petrus Cousins, but you can call me Arno. I'm going to be talking to you today about quantum field theory. Quantum field theory states that all matter and particles act as waves. Thus, matter is a permeation of its corresponding field. Let's look at this pond, for example. If we throw a rock into it, it permeates the field. This permeation, or the wave, is a particle. So if the pond is an electron field, the permeation would be an electron, and if it were the Higgs field, it would be a Higgs boson. The theory states that there is a probability of finding any particle in a certain place. This actually means there's a small chance that I'm here, small chance I'm there, and a near infinitesimal chance I'm there. Okay, so back on Earth. The wavelength of the wave function describes the probability of finding a particle in that place. The wavelength can be determined by the de Broglie wavelength postulated by Louis de Broglie in 1924. The equation is lambda, which is the wavelength, equals h over momentum, and h being Planck's constant at 6.63 times 10 to the minus 34 joule seconds. I will now do a quick calculation comparing the wavelength of a human with mass 100 kilograms and an electron, both traveling at 1 meters per second. As you can see, the human would have a wavelength of 6.63 times 10 to the minus 36 meters, which is smaller than the Planck length. And the electron would have a wavelength of 7.27 times 10 to the minus 4 meters, which is close to a millimeter. The Planck length is the shortest theoretical measurable distance at 1.62 times 10 to the minus 35 meters. Thus we have a very certain position, but this allows for particles in the microscopic world, like the electron, to have a range of possible positions. This gives rise to another theory, the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that not all aspects of a particle can be known to an exact accuracy. The uncertainty of position times the uncertainty of momentum cannot be less than h bar over 2. H bar is Planck's constant divided by pi. This can be visualized with two balloons with the uncertainty of position and the uncertainty in momentum. If you try and decrease the uncertainty in the position, it increases the uncertainty in the momentum, and if you try and decrease the uncertainty in momentum, it will increase the uncertainty in position. This means that the uncertainty in momentum times the uncertainty in position must be greater than 1.05 times 10 to the minus 34 divided by 2. This is of little consequence in the macroscopic world, since h bar over 2 is so small, but this is very concerning in the microscopic level, since you can't know both the position and the momentum accurately. The Heisenberg uncertainty principle actually has more pairs like position and momentum, called conjugate pairs. One of the other most intriguing to me is energy and time. So if you know the time accurately, you can't know the energy accurately, and vice versa. This allows for particles to pop in and out of existence as long as they don't stay for long. One more interesting fact of particles acting as waves is the double slit experiment, first done by Thomas Young in 1801 to show light was a wave and not a particle as Newton believed. This experiment is where a barrier with two small slits is exposed to a beam of light. Thus, if light were a particle, it would make two patches of light on the wall, but since it is a wave, it made an interference pattern due to the fact of constructive and destructive interference. This is like when two small stones are thrown into a pond and the waves cancel. The interesting thing is when electrons are fired at the same barrier, they also make an interference pattern. Even a single electron will make the interference pattern. Thus, it shows that it's interacting with itself. Until we understand these phenomena better, we'll try and get the most out of what science already has to offer, and we'll strive to understand the world better. Thanks for watching.